Hello, this is Dr. Muhammad, and this is another video under Dynamics of Structures under multi-degree freedom systems. And today I'm going to talk about the normalization of mode shapes. Last lecture I mentioned that it is going to be included in the previous video, but actually I found that the length of the previous video is going to be long if I added normalization, so I prefer to separate it in a separate video. Okay, so now let's start with the normalization of mode shapes and what is the meaning of normalization in general. We mentioned before, or we mentioned earlier that vibration mode amplitudes or modal amplitudes, they are commonly arbitrary, means that they are uniquely defined, means that we are, if we have like A1, A2, A3 and so on, they are having the relative values but not the absolute values. So this means that they are uniquely defined, and we cannot obtain, or we are not able to obtain, the real values of the amplitudes. So based on that, we are going to think about something else, which is related to normalizing the mode shapes. So if we have the mode shapes A1, A2, A3 and so on, we are going to look to these amplitudes and we are going to normalize them. Means that we are going to choose one specific value, which is supposedly to be one of the amplitudes that is having particular or is always related to something that we like to normalize to. For example, A1 it is the first degree of freedom amplitude. We like to see it, for example, as 1, and we want to see the other degrees of freedom amplitudes to be ratios of this one. So it is 0.9, 0.8, for example. So this means that it gives an indication for us for the relative values of the other amplitudes with respect to this particular amplitude that we are interested in, because the relative values in general are like meaningless for us. If I put, this is for example 0.0059, this is 0.0067, this is 0.0031, so you cannot distinguish what is this exactly, which one is bigger than one than the other, and how we can find which amplitude is relatively to the other, how much it weights of the other, and so on. So it is better to normalize. From here we use the word normalization, like anchoring the results, letting one result to be clearly unified or unit, and the others are going to be ratios from this unit. So this gives us a good way for understanding the amplitudes in general. Okay. The relative values of the mode shapes amplitudes may be scaled or normalized as required. So the normalization, it is, as we said, it is based on our preference. It is based on you. There is no, we cannot say that there is a method or a particular method that must be used. Rather, there is different methods and you may choose from. Okay, so there are like different ways for scaling or normalizing, as we are going to see in the coming few minutes. There are 3 common methods for normalization, and as I said, they are common methods that usually the people or the engineers and students, they like to use them. Okay, let's clear and go and understand these 3 different methods. So here, the first method, we have, as I said, 3 methods. The first method is the amplitude of 1 degree of freedom system. Generally, it is the first. Generally, it is the first. As I said, if we have A1, A2, and so on, this is the first amplitude. So this amplitude of the first degree of freedom, we are going to set it to unity. So it is going to be equal to 1, and then we are going to normalize the remaining. And the other amplitudes are determined relative to this reference value. So it is going to be ratio from it. We cannot find 1.2 or 1.3. No. always, yes, we are going to find, maybe if we are going to normalize with respect to this, though, we are going to expect that this amplitude of the degree of freedom, or the first degree of freedom, is going to be 1, and we're going to see what are the values of the other amplitudes at the different, or at different degrees of freedom in relation with this one, the first amplitude, the first degree of freedom amplitude. So maybe we can find 1.2 or 1.3 or whatever. The second method, it is the amplitudes are normalized relative to the maximum. Here we are going to look to the maximum. For example, if we have amplitudes like this, like 0.2, 0.4, and 0.6. So these are the relative values of the amplitude. Many cases, whenever that we look to the mode shapes, we are highly attracted to the maximum value, the maximum amplitude. So this maximum amplitude here, it is the degree of freedom 3 at the third degree of freedom, 0.6. So we are going to put it as 1, and then we're going to put this relative to it. So we're going to say this is 2/3, for example. This is like 1/3 of it. So whenever that you look to the vector, you can tell directly that the degree of freedom, or the third degree of freedom, is going to be dominant here, or at least it is it has the highest amplitude, highest value, and the others are less. If we are going to have, for example, something like this, if it's here 0.6, here 0.2, here 0.4, this means that the first degree of freedom, if we're going to normalize it using the second method, it's going to be 1 here, 1/3 here, for example, 2/3 here. So this means that the maximum amplitude is located, or going to be found, in the first degree of freedom. So now we have an idea about the other. Here in this case, other amplitudes, or the ratios, are going to be always less than 1. So we cannot find 1.2 or 1.3 or 1.4 for the others. No, only the first, or not the first, the maximum is going to be 1, and others are going to be relative to this 1. Okay, and because of this one is going to be the maximum, others must be less than 1. Okay, and now the third method, which is important one and most commonly used actually for software programs and so on, it is by adjusting each modal amplitude to the amplitude, this is what we call it phi j, vector phi j, which satisfies the condition, this condition. We're going to look to this condition and we are going to understand it. There is one important hint regarding this way of normalization, that it is usually used in computer software programs. So whenever that you are using different softwares for obtaining the mode shapes, modal amplitudes, and normal modes, like SAP 2000s, ETAPS, or StatPro, or MIDAS, or OpenSeas, these kind of softwares, they are, or usually they are, or they like or prefer this type of normalization. And we are going to see why later on, because it is going also to simplify the computational effort. It is going to simplify the computational effort. As we said, it is sometimes in modal superposition, or in solving the dynamic problem of the multi-degree freedom system, sometimes we are going to find this, these terms are going to be multiplied, or the dot product of these vectors with the mass matrix, for example. So in this case, we are going to normalize our mode shapes such that the mode shape, okay, after being normalized, phi j, it is going to be the amplitudes in the mode shape vector after being normalized, transpose times the mass matrix times, or dot, the vector of the normalized mode shape. Okay, this is the dimensions of it. We are going to find that it would give us 1 at the end. It would give us 1. So we are going to use a technique in order to normalize our common mode shape A1, A2, A3. We are going to normalize it, as I'm going to explain in a minute, to normalized mode shape, which is phi 1, phi 2, phi 3, where this vector, this normalized vector, if we transpose it and multiply dot product with the mass matrix and then dot product with the normalized mode shape, it is going to yield 1 at the end. It is scalar value. Vector transpose times matrix times vector, it would give you one scalar value. If this is 1 by n, where n is the number of degrees of freedom, mass matrix n by n, and the normalized mode shape is going to be n by 1, so we are going to reach 1 by 1, which is scalar value. Let's assume this is equation 7. This can be done by how we can transform our normal mode to normalized mode, or our mode shape to normalized one, in this case, for case number 3. This can be done by computing the scalar factor NF, normalization factor. We call it normalization factor, NF. Okay, this NF. So how we can compute this NF? So NF J means that for mode shape J, it equals to the radical of, or the square root of, this dot product, which is the mode shape itself transpose times the mass matrix dot the vector of mode shapes. So vector of mode shape, or the mode shape vector transpose times the mass matrix, or dot the mass matrix dot the mode shape vector. All of them, they are going to be under the radical. Why they are under the radical? Because they are going to yield what? Exactly, scalar value. So in this case, we are going to get the normalization factor for this mode shape, okay, J, by having the radical of this dot product, okay, where A, J in this case, any arbitrary modal amplitude vector, any modal amplitude vector, any mode shape, okay. So this is how we can obtain this NF, how we can obtain this NF. Okay, now let's go to the next point and highlight what we are going to go with, or how we are going to go with this type of normalization. So the normalized mode shape is going to be phi j equals to the unnormalized mode shape, which is AJ, for example, over the normalization factor. So we are going to divide our mode shape with the normalization factor that we have obtained, as we discussed in the previous slide. Okay, this leads to set of normalized mode shapes phi j, and can be arranged in columns of the matrix. This is what we call it, the normalized or the normalized mode shape matrix. What is the point here? We are going to arrange this normalized mode shapes in columns. So each column here is going to be related to one mode shape. So here, for example, it is the normalization of the first mode shape, which is going to be 1, for example, and this is for the second mode shape, and so on. This is going to be A, J, and this is going to be A, and if we have n mode shapes. Okay, this is here, we're not this is the unnormalized one, so we're going to normalize it first by using the normalization factor, and then we're going to put it in this matrix. This matrix, the whole matrix, we call it the normalization, or the modal matrix. The modal matrix, we call it the modal matrix with big phi, as you can see here, and these are normalized amplitudes for all vectors, arranged in this way. Okay? Okay. So still the point behind this is not very clear for us, why we need to do all of this. Okay? So the point is in this case, the orthogonality condition in general can be expressed as, so we are going to revisit the orthogonality condition. If you do not know about orthogonality condition, please revisit the previous video. I explained it in detail. Okay, so the orthogonality condition now is going to be expressed in this form. What is the form here? If you remember, we said that the normalized, or we are going to say that the normalized or the normalization or the modal matrix transpose times the mass matrix times the modal matrix is going to give us the identity matrix. What is the identity matrix? All the diagonal elements are going to be 0, and all the off diagonals, they are going to be all the diagonal elements, they are going to be 1, and all the off diagonal elements, they are going to be 0. This is what we call it diagonal. This is what we call it the identity matrix. Identity matrix. Okay. If we multiply this equation, if we are going to multiply this equation, if we are going to multiply this equation by the vector of circular frequencies, okay, the vector of circular frequencies, then we are going to have we are going to get this vector is omega squared, the vector of omegas. So this means that if we have like omega 1 squared and omega 2 squared, omega 3 squared, this means that the circular frequency squared of the first mode and the circular frequency of the second mode, and so on and so forth. So if we are going to multiply the left hand side of this equation and the right hand side with this vector, let's see what we are going to obtain. So we're going to multiply here the omega squared vector. We're going to put it here before M matrix, and we are going to put it here in the right hand side, which is omega squared, the vector, times the identity matrix, times the identity matrix. Then we're going to find that if you look deeper to the left hand side, whenever we have omega squared times M, okay, this means what? K. Do you remember this this from the single degree of freedom system? Do you remember it? Do you remember that we have, whenever that we have omega squared, it has a relation between the stiffness and the mass, right? Omega squared equal to K over M, right? So here it is the similar case. It is a similar case. Omega squared as a vector is going to be multiplied by the matrix, the mass matrix. This would give us the stiffness matrix, and you can try it if you want. We're going to find it, or we're going to find it through the examples later on. Okay, and here we are going to multiply by phi again. So let's put everything as it is. This big phi, which is the modal matrix, as it is, and here it is the modal matrix transpose as it is, and these two vector times matrix, it is going to give us the stiffness matrix. So this gives us the left hand side is going to be modal matrix transpose times stiffness matrix times the modal matrix again equals to the right hand side is going to be omega squared times the identity matrix. So as you know that the identity matrix, it has only 1 at the diagonals, right? And everything of the diagonal it is 0. So whenever we multiply the vector, if we have the vector here omega 1 squared, omega 2 squared, omega 3 squared, and so on, then we're going to obtain that we will get this diagonal matrix of eigenvalues. So we're going to have here omega 1 squared, here omega 2 squared, omega 3 squared, and so on. Okay, and all the elements outside of it's going to be zeros. So this is what we call it, the diagonal matrix here, the diagonal matrix of the eigenvalues, omega squared. Okay, the omega squared or the diagonal matrix of eigenvalues omega squared. Okay, now we can end up with something that is interesting for us. That is, whenever we have the modal matrix, we need to remember something, that this equation is going to give us the identity matrix. This is also going to greatly simplify the computational or reduce the computational effort, because we are going to have the normalized modal matrix, or the modal matrix transpose commonly encountered terms in the dynamic analysis of multi-degree freedom system times the mass matrix times the modal matrix again. It would give us the identity matrix. And if we find this, which is the modal matrix transpose times the stiffness matrix times the modal matrix again, then we're going to have the eigenvalue or the eigenvalues matrix squared. Okay, so which is the squared eigenvalues on the diagonal, and everything of the diagonal it is going to be 0. Okay, so remember that our orthogonality condition now transformed to be in this way. Okay, which is, as I said, it is going to simplify the process of the dynamic analysis solution for the multi-degree freedom system. Okay, so now we are there. We understood now how we can obtain the orthogonality condition using our normalization of, or third method of normalization. Let's go to the next. Okay, and put some summary for what we have explained regarding the orthogonality and the normalization, because they are important. So we can say summary of the orthogonality condition with normalized mode shapes using the third method, which is using the normalization factor of the radical, as we said. A transpose, the modal shape transpose times M times the modal shape vector again. This is the NF, which is the third method. This is what I want to say is the third method. So in this case, with respect to the mass matrix, okay, we are going to have two cases here, okay, commonly encountered, as I said. Whenever that we have one vector I transpose multiplied by the mass matrix multiplied or dot product with the same vector, take care, they are, as I said here, they are like different vectors now. Sorry for this, mean that two different mode shapes, okay, I and J. This is two different mode shape vectors. In this case, this multiplication is going to be exactly 0. Okay. And the second case, if we have the same left hand side here, but instead of having two different mode shapes, we're going to have the same mode shapes, which is phi transpose of J dot mass matrix dot the phi of J, it equals to 1. This is for what? The same mode shape vectors, or vector, the same mode shape vector. Here, this one, it is the same as this one, only this is transpose, okay? But here, in this case, here, if they are two different mode shapes, these, the dot product here, or the scalar output here is going to be, if this is I and J, any two mode shapes, it is going to give us 0 here. Okay. This is, as I said, very important and going to simplify everything. Simply we put all of this going to be 0. Simply we're going to put all of this to be 1. Okay, that's greatly simplifies the issue for us. Okay, so remember that this was for mass matrix. Now let's assume, or let's go with whenever that we encounter something, but instead of mass matrix here, we are going to have exactly, stiffness matrix, what will happen here? So let's see. In case of stiffness matrix, we are going to have also the same with respect to stiffness matrix. In the middle, we are going to have K matrix, and here, the two sides here, the dot is going to be phi I transpose times stiffness matrix times phi j. It equals to 0. Okay. And in the second case, if we have phi transpose j, and here is j, means that they are the same mode shape vector. The output here is going to be omega squared. The output is going to be omega squared, and you can prove this. You are going to find that it is by default it should yield omega squared here, not 1. In the case of the mass matrix, it was 1 here, but here it is going to be omega squared. So this, as I said, greatly simplifies the solution process of the multi-degree freedom system when we are solving it dynamically. Okay, so I hope that we have understood now the meaning of the normalization and the orthogonality condition for these cases with respect to stiffness and with respect to mass. Okay, now let's go to the next, which is going to be an example for us. It is going to be an example for us. Okay, and this example is giving us the, sorry for this. Okay, so this example is telling us that we need to normalize the mode shapes obtained in the previous lecture using the three methods of normalization of mode shapes. So we have 3 methods, and already we have from the previous example, not in the previous lecture directly, the like 2 lectures before, the multi-degree freedom system example. And anyway, I put the mode shapes here, the amplitudes of it. So mode shape number 1, we call it A1 here, equals to 0.6 and 1. And the mode shape number 2, it is going to be which is A2, okay, and we have 2 degrees of freedom for the example. This means that we have here for mode shape 1 found that the values of the amplitudes were 0.6 and 1, and for the mode shape 2 it was minus 1.63 and 1. So if you remember, we said that we have like 2 different modes, which is it was mode 1 here, it was 0.6 here and 1, and for the second mode shape it was something like this, which is here minus 1.63, and here it is 1. So we said that we are having 2 different mode shapes in our case with these values of amplitude, Okay, so now let's go and try to solve the equation, or solve and normalize our mode shapes. So first of all, let's use method 1. Method 1, we are going to use mode number 1, where in this mode we are having 0.6 and 1, as we said, 0.6 and 1. This is the mode 0.6 and 1. So we are going to normalize based on the first degree of freedom. Now the first degree of freedom, which is A1. So we have A1 and A2. So A1 equals to 0.6, A2 equal to 1. In the first method of normalization, we look always to the first mode shape amplitude, which is A1, and equate it with 1. So we need to divide 0.6 by another 0.6. So we did this. 0.6 divided by 0.6 equal to 1. And for A2, we're going to have 1, which is already the amplitude of the degree of freedom number 2, 1 over 0.6, it gives us 1.62. Okay, so based on this, A1 normalized, we call this is between the parentheses here means it's a vector, and then we put the subscript, which means that it is normalized. Okay, it is normalized. It equals to 1 here, the degree of freedom 1, and 1.62. So now this vector is normalized vector. This vector is normalized vector, where that unity is obtained in the first degree of freedom system. First degree of freedom. And here in the second, it is the second degree of freedom. How much relative to the first degree of freedom coordinate? Okay, it is 1.62 here. This is for mode 1. For mode 2, we have the values of mode 2 minus 1.63 and 1, and we are going to divide it by the value of the first mode as it is, minus 1.63 here and minus 1.63 here. This gives us 1, and the second mode, it is going to be minus 0.61. Based on that, A2 normalized is going to be 1 here, which is the unity, as we said, the first degree of freedom, and here it is going to be the second amplitude after being normalized, which is minus 0.62, minus 0.62. Let's go now to the second method for normalization, which is related to the maximum. We are dealing with the maximum here, the maximum value. We want this maximum to be 1, and the others are going to be relative to this one. So first mode shape, as we said, 0.6 and 1. We found that the maximum here is 1, which is already what we want. So no need to make any normalization. This modal amplitudes are normalized by default, so already normalized. So A1 after normalization, which is no difference between it before and after, actually, is going to be 0.6 and 1. Why? Because the maximum value is 1, as we want. Mode 2, we have, as we said, 1.63 and 1. Then we want, which one is the maximum here? The maximum, take care, it should be the absolute without the sign. So we have 1.63 here. We're going to normalize it and divide it by the maximum value of the 2. The maximum value here is 1.63 over minus 1.63. It is going to be 1. And the other amplitude is going to be minus 0.6. This means that A1, sorry, this is not A1, this should be A2 here, because this is the second mode shape. A2 is going to be normalized by this method, and it gives us 1 here and minus 0.6 here. Okay. Let's go to the third method. Okay. So in the third method, we are going to have method number 3, which is we need to calculate the normalization factor, if you remember. And after normalization factor being calculated, we are going to have A1, vector A1, it is going to be divided by NF, and then A2 going to be divided by NF. And here NF1 and here NF2. So we are going to have like normalization factor for each case, right? Okay. So here NF1 squared based on the equation, because before it was under the radical. So we removed the radical from here and we put squared here. So NF1 is equals to A1 transpose times M matrix times A1. We are going to take the values from the previous example that we have explained before in 2 lectures before. A1 transpose is going to be 0.6 and 1. This is transpose, as you can see. Times the matrix, we had, if you remember, we had 2 degrees of freedom. The masses here was 1, 2, 2, 4, 4.9. Same here. So this was M, and here also it was M. Based on this, we are going to have the diagonal matrix of M. This is M here. Everything is 0 of the diagonal times the modal shape, 0.6 and 1 here. If you are going to multiply this using dot product, it's very easy to obtain the scalar value here. Okay, 16,951. Based on that, the normalization factor 1 equals to the square root of 951, which is 130. So this is NF1 that is going to be used for normalizing mode shape 1. Okay. Okay, now let's go to the next. And in the next, we are going to put the normalized mode shape, the normalized mode shape. A1 normalized is going to be 0.6 over 130 and 1 over 130. This gives us this value, 0.0048, 0.0077. So this is the normalized mode shape, the first mode shape, and it is normalized. In a similar fashion, okay, we are going to obtain the NF2 for mode shape number 2. Okay, so you are going to find that it equals to 208.8. So please calculate it by yourself, consider it as an assignment, because you're going to follow the same steps exactly that I have done for the first mode, and you are going to obtain this value. So please do it and check this value if it is right or not. So similarly as before, we're going to have this NF2. Based on that, the normalized second mode shape is going to be minus 1.63 over the normalization factor 2, and this is 1 over 208.8, the normalization factor. This gives us this normalized. This is A2 normalized, minus 0.007, and this is plus 0.0048. As you can see here or here, we do not have like 1, okay, and fraction of 1. It's not like this, because this value is normalized in order to obtain a specific way, which is, as we said, AN transpose times M, okay, and A. This is what we want to have, okay, and equated with the values that, or to simplify our method for the solution. Okay, so at the end we want to have this as the normalized factor, or the normalization factor, in order to obtain the orthogonality condition in a way that can help us in making the solution better and easier. Okay, now let's go to the next. So the modal matrix, in this case, we are going to finish with this. So here we are going to arrange what we have obtained in what we called it the modal matrix. So this is the modal matrix here, and we're going to arrange the two values coming from the normalized first mode and the two values coming from the normalized second mode, as we obtained it here. So this is what we call it the modal matrix, the modal matrix. Now this is an assignment for you if you want to check it by yourself. Please, this is the modal matrix, and you have the mass matrix before, and you have also the stiffness matrix of the example, right? So check that this modal matrix that you have obtained now, transpose times the mass matrix times the modal matrix, it would equal to the identity matrix. Please check it by yourself. Make this dot product and you are going to obtain the identity matrix to check that you have understood what we have gone through up until now. And this is with respect to the mass matrix. Now do the same with the stiffness matrix, and then check what is going to be the output. The phi transpose dot k dot phi, it would give to you the eigenvalue squared matrix on the diagonal only. Already these values, already we have obtained them before, in the previous example in the previous lecture, right? So based on that, please check and let us, or this is only a kind of verification for you that you have understood the mathematical manipulation of the data and you are able to understand what is the meaning of the orthogonality condition and normalization. This brings us to the end of this video. I hope that you have understood what I have said for today. I'm going to recap what I have mentioned now. We started with the normalization, and we said that we have three different methods of normalization that we need to know them. The first one is related to the amplitude of the first degree of freedom. The second is going to be related to the maximum displacement. We are going to make it as 1, and then the others are going to be less than 1. Here we are going to make the first degree of freedom to be 1. Others are going to be relative to this value. And the third one is going to be related to adjusting the amplitude of the modal amplitude, going to be adjusted to be phi j, where this phi j is going to satisfy this condition, which is the after normalization phi j transpose dot mass matrix dot phi j equals to 1. Okay, based on that, in order to obtain this after normalization, we need to normalize our mode shape with normalization factor. We call it NF, and this NF, we mentioned that it would equal to the radical of AJ times or transpose dot mass matrix times AJ. This is the end of this video. I hope that you have understood it. It's important, and we are going to build upon it for the next videos. Normalization and orthogonality conditions are going to help us a lot for what we are going to explain in the next videos. Thank you, and see you next video, inshallah.